You know what? I've got a thread spool. Actually, it's quite awesome. So, okay, let's get started. I will put this thread spool on the table, and I will pull the thread. And let's vote. When I pull the thread, will the spool go that way or the opposite way? Now, I can't see you, everyone there. Just show with your hand which way it's going. This way or that way. Just point. Okay, most people are pointing that way. And you know, physics is not a matter of voting. The thread comes from below. It goes to the right. On the other hand, I'm a little bit of a nasty guy. You know, let's do it again. I put the thread horizontally, I pull it, it goes that way. I leave the spool on the table, it goes the other way. I can actually choose which way it goes. And the funny thing is that it's not the tension in the string which makes the spool move. It's the friction. Yeah, it's the friction. This is, as my grandmother used to say, higher mathematics. No, it's not. But you need to be able to deal with rotating things and stuff and Newton's second law, so let's not go into that. But this is a nice party trick. You can use it, perhaps win some money. Okay, so this show is actually dealing with most of the different areas of physics. Mechanics, we already got started. We will continue with mechanics. Then, well, tonight I'm mainly performing unplugged. So despite of that, I will do some electromagnetics also. And towards the end, a little bit of quantum mechanics. Okay, so you may or may not have heard about the falling rod paradox. So I got a rod, just an ordinary plank, and I got a nut. I will put it against the screen. You can see that there's something in my hand here. It's a nut. And the falling rod paradox, what is it? Well, it says that if I have a rod and release it, the tip will move or accelerate faster than g. And I'm going to prove it. I will put the nut here at the end, and I have a cup which is empty. And if the end of the plank is really moving faster than g, yeah, well, what happens is that the nut will fall behind. And if we are lucky, it will go into the cup. Okay, let's see what happens. Where's the nut? Inside the cup. All right, so it worked. However, acceleration is rather a quick process. So you can't really see what's happening. So that's why we are going to use a high-speed camera. But before doing that, let me explain what we are about to do. Okay, so we have the rod. Let's put some beads all over the rod and release it and take a video of it. Now, if the rod is falling faster than g, the beads should be left behind. If some part of the rod is falling with the same acceleration as g, the beads will stay put. And if it's slower, they will also stay put. And now, okay, obviously the tip is moving faster than g, but there must be some point where the acceleration is exactly g. So we should see some kind of breaking point there. And now I'm going to ask you, we are going to watch a video in a moment, but I'm going to ask you which way the beads, I mean, you can see the beads in the air. So will they form a straight line? Will they fall a parabola like this or parabola like that? You can use your hands to show you what you think it will be. Okay, I see a lot of parabolas here. I see some straight lines, and I see parabolas both ways. Okay, could you please start the first video? This is taken with a high-speed camera. This is the rod, and you see the beads. It takes some time. There's the release. And the beads, they form a straight line. And you can see this point is moving with the acceleration of g. Okay, that's nice. You can see it actually. The tip is moving fast. Now, before starting the second video, let's make it move faster. I mean, you always should up your experiment. I want to make it move faster. So I'm going to ask you a simple question. Okay, this is the hinged end, this is the free end. I will put a mass somewhere on the rod to make it faster. Should I put it here? If you think so, vote now with your hands. Or claps, okay? Or should I put it somewhere here? What do you think? All right, all right, all right. So let's look at the second video. Because the solution is already recorded. Now here's the mass at the tip. Nothing really happens. I mean, the beads, well, there is always one guy who's against everything else, but basically they stay put. That means it becomes slower. And that's kind of weird. We put a lot of weight in the tip and it becomes slower. Okay, think about that for a while. And let's do a second experiment, the third video. Okay, and in this case, all the beads are nicely near, almost all of them. So it becomes faster when the weight is closer to the hinge. All right, that's nice. And slightly bewildering. All right, so next, let's do some electromagnetics. We already saw the first show with a copper tube. And I'm going to continue from that because I have a copper tube which has been sawed open. Can you see that there's a small slit here? I can put this kind of spoon in here. So it's sawed open all the way. And it's a tube. And I have a magnet. And now the way it was shown earlier to you, when the magnet is moving inside the tube, there's a current flowing. And now we have cut it open. So will the current flow? Will the magnet will be slowed down? What do you think? Vote now if you think it's slowed down. Okay? And I assume most of you, yeah, I saw, thank you. Most of you assume that it won't be slowed down. So let's try it. It is slowed down quite a lot. So why is that? Well, it means that the current is not going that way, actually. It's going some other way. It's a little bit hard to imagine, but I can use this one. Let's imagine that this is the edge of that copper. So the current is actually doing a nice loop inside the walls. That's why it still works. Now, I would like to do a little bit of a competition here. And actually, I don't like competition very much. I was never good at them at sport, and I didn't like to take time and so. But nevertheless, let's do a competition. So I will need someone who is voluntary. Okay, please. And I have two copper tubes. You can see that they're tubes. Okay, and I have two sets of magnets. So I'm going to give you one set of magnet like this, and I'm going to give you a tube like that. And on the count of, I'm going to say 3, 2, 1 now. When I say that, you will put the magnet through the tube, and we will see which one is faster. Actually, no. We are going to see which one is slower, because the slower one is the winner. Okay? There's, you can see it's equal. No difference. Okay, so can you stand here so the audience can see you? Okay, let's do this together. 3, 2, 1. Duncan. Okay, you are the winner. Your tube was slower. You had a better tube, so thank you very much. Why is that? They have the same wall thickness. They have the same length. Why is that? Any suggestions?
Different magnet.
Sorry?
Different magnet.
No? Yeah, you're right. We should have exchanged magnet and done it once more, but I can assure you magnets are identical. That's not the solution. Well, you may have seen that one of these is yellow. It's made of brass. And brass does not conduct electricity as well. It means that the current inside the brass walls are weaker and the magnet is faster. That's the solution. The fact that we have very dim light here is good because I think you cannot see the difference between the tubes. All right, so mechanics, electromagnetics, and then quantum mechanics. And so far I prefer unplugged, but at this stage I will be needing a little bit of electricity nevertheless. Okay, so I need a light source. And now in my hand I have 4 pieces of plastic. There's one which is red, one is orange, and one which is green, and the last one which is blue. But I'm going to claim that the red one is not red, the yellow one is not yellow, the green one is not green, and the blue one is not blue. Because the colors you see are not actually the plastic, but there is some process going on in the plastic. And that process is started by this light I'm shining on them. And also, I cannot show you very much quantum mechanics, but I'm going to say that, or claim that various lights have different amount of energy. You heard a lot about energy today, and now I'm going to prove you that blue light has the most energy, and red the least. So if I put the light like this, I hope you can see all the colors. Blue, green, orange, and red. Right? Okay. So what actually is happening here is that the white light is hitting the blue light. The plastic which is seemingly blue. And then the process produces blue photons, light quanta, which hit the plastic which is seemingly green, and it starts to emit green light, and so forth, until we reach the red one. Because, in fact, I would say all of them are red. And what I said in the beginning, that the green is not green, the orange is not orange, but they are, for instance, they could be red. It's true. Because when the white light is shining on the red one, I get red photons. And the red photons, they are weak. They can do nothing, but of course they are spread everywhere. So they are spread to the other plastic. If I go this way, I see all the colors. I can, if I like, I can go stepwise, like so. And you see, when I shine it directly on the yellow one, the green one becomes yellow, but the red is still red. This is nice. Is this something magical going on? No. This is something which is called fluorescence. And fluorescence is actually quite common in nature. And if you like ice cream, you do. Excellent. Okay, we are in Switzerland, but I'm going to do a little bit of advertisement for the Italian ice cream, because they're using spoons which are fluorescent. So these spoons I got when I was eating ice cream in Firenze. And they are fluorescent. So you can do exactly the same thing with them. So you can use your mobile phone. Actually, I can use my mobile phone now so that you see that it is actually quite possible. Could we dim the light a little bit? Okay, so I'm going to shine on the green one. And it's not so easy, but you can see both the green and the orange one. Okay? I hope so at least. But if you go on the orange one, you should not be able to see the green one anymore, because orange light has less energy. If you compare this one with that one. So, after the show, go and reward yourself, buy some ice cream, and ask for a fluorescent spoon. Okay, they will not know what it is, but you will know it when you see it. All right, that concludes, actually, there's only nuclear physics and thermodynamics, which I didn't have time for this time, so thank you very much.